In this lecture, we will be dealing with k-nearest neighbor classification. As usual, we will start with the summary of the last week, and then we will start working on KNN, and then we will be seeing dimension reduction. So last week we worked on decision trees. We worked on how to construct a decision tree, how to display a decision tree. We have seen something called Gini impurity index. We said we use Gini impurity index in order to construct a decision tree from a table value. And then we have seen we can use decision trees for regression as well. And then we worked on something called grid search CV, which exhaustively search over specified parameter values for an estimator. Then we have seen how we can basically deal with categorical data for our classification problem. And then we have seen how we can deal with missing values. So coming back to decision trees, basically we ask a decision tree a question, and depending on the answer we make a classification, such as the height of a person. And if the person is taller than 180 centimeters, then we classify that person as tall, as on the left side of the tree. And if the person is shorter than 180 centimeters, then we classify the person as not tall. And the tree doesn't need to be 2 levels. We have seen that we can have a much more complicated tree, and we can have both numerical data and we can have categorical data within our tree. And we have seen some definitions for the tree. We said that all these blobs are called nodes, and the one at the very top is called the root nodes, and all these lines are called branches, and all these last nodes, or the nodes with red, they are called leaves, decision leaves. And all these levels represent the levels of the tree. Okay, in this case, this is root node stands at level 0. This is level 1 of the tree. This is level 2 of the tree, and this is level 3 of the tree. Then we have seen something called Gini impurity index in order to construct a tree from table data. This is measuring the impurity inside the tree or inside the data, and if the impurity is low, that's something good, and if everything is from the same class, then the impurity is low. If there are some other elements or other classes inside the data, then medium impurity we have, and then if there are too many classes, we have high impurity. And the way we calculate the Gini impurity index is we take the probability of picking 2 distinct elements. Okay, in this case, for example, we have 10 elements here, and we have 10 elements here as well. Since this set is more uniform, we have just 2 classes, the probability of picking the same element is higher, and the probability of picking distinct elements or different elements is lower. As you see, we draw 10 couples from this set, and we draw just 4 out of 10 with different elements. But since the number of classes is 4 here, it's higher probability that we draw different elements from different classes. Okay, for example, in this experiment we draw 7 out of 10 different elements, such as this one, such as this and this one. Okay, and the way we calculate the Gini index is we basically create a table, and then it is 1 minus the area of selecting same elements. In this case, the total area is 10 by 10, it's 100 since we have 10 elements. Okay, and we have this area, it's a 4 by 4, which is 16, that's 3 by 3, since we have 3 same elements from this class, we have 2 different elements from this class. We take this area and then we take this area. Mathematically speaking, we have 1 minus the blue area plus the red area plus the green area plus the yellow area. Okay, and in this case it's 0.7, the Gini index. Then we have seen how we can basically construct decision trees. We did 2 examples, and what we have seen is decision trees have a tendency to overfit. Okay, this is an example of overfitting. And there are so many leaves. These 2 trees were from the same example, from the iris datasets. In one case we use the petal length, in the other case we use the sepal length. They are basically from the same dataset to different sets of independent variables. In this case the tree looks okay, and this is the decision boundary of the tree, but in this case it's far beyond the supposed level. Okay, this is not a good tree. There are so many branches, and this overfitting problem may occur with the regression as well. We have seen if we do not assign some regularization parameters such as the mean sample leaf, as in this case, the decision trees have the tendency to overfit the data if we use them for regression, and especially if we use the maximum depth a little bit higher than it should be. Okay. And then we have seen how we can deal with categorical and missing data. We did an example. We have seen there were some missing values and there were some categorical values. The missing values, we filled them with the median of the cell. And for categorical data, we use something called get dummies from pandas or one-hot encoder from scikit-learn, which was converting all the categorical data into numerical data. Okay, revisiting the quiz of the last week, Gini measures the impurity. Since it's an impurity index, decision trees can handle categorical and symbolic data. That's true. Decision trees can't handle numerical data. That's false. They can basically handle. Which one is the strategy to select the root node for decision trees? We basically select decision with lowest impurity. Decision trees can be used for regression and classification. That's true. Which of the following decision trees are decision tree algorithms? They are all decision tree algorithms. Which of the following are kernels that are used for support vector machines? All 3 are basically kernels for support vector machines. A linearly separable classification problem can be solved by using a higher dimension of the feature vector. That's basically the definition of support vector machine. If it's linearly inseparable, then we use a higher dimension in the dot product, if you remember from 2 weeks ago. Decision trees can handle unbalanced data very well. That's false. You need to have balanced data for your tree, otherwise it has the tendency to overfit. If a decision tree goes too deep, the probability of overfitting may increase. That's true. Alright, K nearest neighbor algorithm or KNN algorithm motivation. We have different strategies for learning. Sometimes we have some constraints. Sometimes we look at the regularity within the data. For example, we have a concept called one-shot learning, or we have a concept like explanation-based learning, or we check the regularity within the data. And nearest neighbors is an algorithm in this category. We check the regularity within the data. That's pretty similar to neural nets and boosting. And KNN is a non-parametric supervised learning and used for classification as well as regression. It's called non-parametric because the distribution of the data is not defined mathematically. It's a lazy learner. That means it doesn't learn a function. Up until now, what we have seen as classifiers or regressors, we created the model and then we learned something from that model, and we could be able to save that model for future use. Okay, that doesn't happen with the KNN. That's a lazy learner. Each time you ask a question, it needs to recalculate everything. So you don't need to train it every time. Okay, let's see how does it work. Okay. Suppose we have two classes, red wine and white wine. So these are white wine and these are red wine. Okay. And we would like to find whether a new class is red wine or white wine. So we don't know from which class this wine is. Okay, that looks close to red wine, but we need a systematical way to make a decision about the class of this glass. Okay, and that's what the KNN does. For KNN, we first determine the k nearest classes or k nearest neighbors. Okay, and geometrically what that means is we basically select first k elements that are closest to this newly coming class. Okay, and in this case these four red wines and one white wine are the closest wines to this newly coming wine, and they are within a vicinity, okay, of this wine. And we use a majority voting on the nearest neighbors to determine the newcomer's class. What majority voting means, since we have two classes in this example, red wine has 4 votes because there are 4 elements from red wine, and white wine has 1 vote because it has just 1 element from this class. Okay, so 4 out of 5, 1 out of 5, that means red wine wins the voting, and this guy is from the red wine class. Okay, let's do some other examples. In this case, we use k as 5. K may depend on your problem. Okay, you can select the k. You can select how many different elements you would like to use as your neighbors. In this case, it is 3 as well, 5 as well. Okay, and we have 1, 2, 3 classes: triangles, circles, and pluses, and we would like to predict the class of this one. That's a much more complicated problem than the previous one because the classes are somehow within each other. And since we select the k as 5, we basically select the first 5 elements that are closest to our newly coming element. And in our case, we have 3 triangles, 1 circle, and 1 plus. And once we do the majority voting, the triangle has 3 votes, the circle has 1 vote, and the plus has 1 vote as well, which means basically the newly coming element, this element is supposed to be from class triangle. Okay, let's look at this example. In this case, this is the newly coming elements. We have 2 classes. We basically selected k as 3, which means we need to find the first 3 elements that are closest to this element, and the majority voting says this guy is from blue class. One thing we need to remember is, depending on the value of k, the class we predict may change. Let's look at this example. Let's say initially we selected k as 3, okay, which means basically we have 2 triangles and 1 rectangle. when we select k as 3. Okay, and that means with the majority voting we have this element from triangle class. But what if we select k as 5? Then we have 2 triangles and 3 rectangles. Okay, which means this element goes to this class, the class of rectangles, which means basically depending on your k value the decision may change. Okay, that's pretty important. Alright, let's see how the algorithm basically works. It's a pretty simple algorithm. We choose the number of k initially, and then we select the distance metric. We will see some metrics basically, but just for now assume that we select the distance metric. We find the k nearest neighbors of the sample. We assign the class label by majority voting. 4 steps, pretty simple algorithm, but it works very efficient and very nicely. And in detail, if we check the algorithm, we first load the data, definitely. We initialize k's to our chosen number of neighbors, and what we have seen is depending on the k value, the decision may change. For each example in the data, we calculate the distance between the query example and the current example from the data. Okay, if something new comes, then we calculate the distance between the newly coming elements and everything else. There are some strategies, obviously. You don't need to deal with everything. That's something we will be seeing. But for now, assume that we brute forcefully calculate the distance between everything else and the query example. Okay, and then we add this distance and the index of the example to another ordered collection. Then we sort the ordered collection of distances and indices from smallest to largest, which means in ascending order, and then we pick the first k entries from the sorted collection, since these are the closest elements to the newly coming elements. Then we get the labels of the selected k entries for majority voting. If we are solving a regression problem, then we return the mean of the k labels, and if we are dealing with classification problem, we return the mode of k labels, which means actually mode is giving you the majority voting of that labels, right? Now let's try to make an example in Python for our KNN problem. Okay, we first import the required libraries. Then we have a function definition of KNN. Okay, let's see what we have. We have our data. So these are our existing data. We have our query example. So this is the one we would like to search for. We have k. Basically, this is our k variable. We take a distance function, and then we take a choice function. So this is a very general function. We could definitely use Euclidean distance, for example, in order to calculate the distance between points. Since we will be dealing with classification problem, we could just use basically the majority voting. But since this is a general function, we are taking these functions from outside as well. So if you remember the algorithm we discussed in detail in the slides, we initially create an empty distance and indices list. Okay, and then for everything inside the data, which are the existing data points, we basically calculate the distance between our query example, query element, and this data point. Right, we calculate the distance, and then we put this distance as well as the index of the data to our lists, to this list. Okay, and remember the fourth point in the algorithm, we basically sort our list with respect to distance in ascending order, and then we select the first k elements from our list, okay, because this is KNN and we get k from outside. We get first k elements and then we get the labels of the selected k entries, okay, and then we basically use our choice function on these k labels and then we return the values, right? So we have different choice functions as we discussed. We could have mean if we are dealing with regression problem, and we can have mode if we are dealing with classification problem. In our case, we will be dealing with basically classification problem. We can have different distance metrics. We will be seeing different metrics basically. But in this case, we will be using Euclidean distance, and Euclidean distance is pretty simple. This is a distance we use occasionally in order to calculate distance between 2 points. And then let's create our data. That's a one-dimensional example. We have point 22 from class 1, 23 from class 1, and that goes on like this. We have 45 from class 0. We have two classes. We have class 1 and we have class 0. Okay. And then we create our x and y. X is basically the first column of our data. Okay, that's what it does. And y is basically the second column of our data. Let's try to plot our data. But let's try to plot our data in 2D. Okay, this was a one-dimensional example. Just to make it fancier, we draw it in 2 dimensions. Okay, we basically use y as x. So this is our data, initial data. If the coordinate we assign is 23, then y coordinate is 23 as well. So we have class 1 here, we have class 0 here. Okay. Now we will query 29. Okay, 29 falls somewhere here. Okay, that's definitely from class 0. This is class 0, right? And it's basically within all these class 0 elements, so it should be from class 0. But let's see what will happen. We select k as 3. Okay, and this is our x and y values. We would like to make the prediction, and then this is the 29, the query elements. And for distance function we use Euclidean distance, and for choice function we use mode. And these are basically the points that are closest to our prediction point, and we basically get class 0 for this example, which is what we would expect, right? Since 29 is here, 29 is somewhere here, that's definitely from class 0, what we would observe. But let's see what would happen if we select k as 9. So this is, when we select k as 9, this is a basically pretty big vicinity that we need to check for. And then, since this element is far away from this cluster, okay, the first 9 closest elements will be from this set. And within this set, we have 5 elements from class 1 and 4 elements from class 0. Okay, which basically means if we select k as 9, the prediction category will be from this class. That might look absurd, but since there are more elements from this class, that's the way KNN behaves. Okay, so you need to be careful while selecting K. Using too small K values is not good. It works pretty fast if you use small K values, but it may do some mistakes. If you select K too big, then it works slowly and it may do errors such as this one. It can assign to a different class. Alright, let's make another example with our iris datasets. That's our flower datasets we usually use within our class. So we initially import the required libraries, and then we basically read the data and assign the column names. And then when we check the first 5 rows of the data, we have sepal length, sepal width, petal length and petal width, and we have the species of the flower. So in this example, we would like to use these 2 columns, petal length and petal width, and this is how we do that. And since these classes are categorical classes, we would like to convert them into numerical classes. That's something we had seen last week. We can deal with that. That's how we do. Basically, since these are the target variables, we don't need to use getDummies or one-hot encoder. We can just assign numbers to the textual classes. So we create our X-train and Y-train values. And this is how we use basically the KNN from scikit-learn. From neighbors, we import KNeighbors classifier. That's classifier because we have regressor as well. And then we basically define number of neighbors for our classifier. Okay, this was the definition phase. This is the fitting phase. This is a lazy learner, but it calculates some trees. So once you define something else, once you would like to make a prediction, it doesn't basically use everything, but it uses some strategies, such as this one, bolt tree, KD tree, or brute force, so that it doesn't need to look everything. If we use brute force as the algorithm, then it checks everything. Okay, if you use a KD tree, it reconstructs a KD tree, and then it's not gonna use everything. It's not compare everything with everything, but it will just use this KD tree as the data structure to make an efficient prediction, such as it's same for the bolt tree as well. It creates some trees, either a bolt tree or a KD tree, and then it doesn't compare your newly coming element with everything else, but it compares more intelligently. Okay, but if the number of elements are too small, it will not create any bolt tree or KD tree because the construction of these trees takes time as well, and it will just use a brute force if the number of elements is too small. Okay, so let's try to get the decision boundaries for our classification, KNN classifier. And the way we do is we will create a mesh grid with the minimum and maximum of X train, and then we will make predictions over our X train. And as you see, we have these decision boundaries. Okay, everything that falls within here would be categorized as from this class. Everything that falls within this category will be categorized within this class, and everything falls within this polygon will be categorized from this class. This class is pretty distinct from the rest too. There are some intersections between these two classes, but as you see, at least in the training sets, the KNN classifier is doing a pretty good job. Alright. So what happens if we select a too small k? As you see in this example, it has a tendency to overfit if you select k too small. And the boundary becomes smoother, which means the probability of overfitting decreases if you select the higher k. But we have seen an example, if we select k too big, then other problems may occur. Okay. So let's talk about this distance matrix. If you remember from the Python example, we assigned Euclidean distance as the distance matrix. So what else we can assign, basically? What other metrics we have? So we will be talking about three important distance metrics today. The first one is Euclidean distance, and then we will be talking about Manhattan's distance, and then we will be talking about Chebyshev distance. Okay. The Euclidean distance is the most common distance. That's basically the L2 norm of two vectors. And that is sometimes called the flying distance as well, because it's the shortest distance between 2 points in 2D or 3D. Okay. If you have a city block, if you have something like this, let's say these are the roads. If you had a car, you need to pass from this road, right? But if you had a helicopter, you could just fly from point A to point B. Okay, that's why it's called flying distance. And it's basically the shortest distance between point A and point B. And the Euclidean distance between point 1, 2 and 3, 3, these are the coordinates of the points. It's calculated as 1 minus 3 square plus 2 minus 3 square root. Okay. And the second metric is called Manhattan's distance or city block distance. That's summing the absolute value of the difference between the elements of the vectors. And if the Euclidean distance marks the shortest route, the Manhattan distance marks the longest route from one point to the other. Coming back to this example, let's say we are here, we would like to go here. This is a city, okay, and these are the roads of the city. And since we don't have a helicopter in this case, we need to move from this point to here. We need to follow the road, and then we come to point B. Okay, Manhattan distance or the city block distance is basically measuring that distance. Okay, and the definition is you basically get the absolute value of the differences and sum them up. Therefore, the distance, Manhattan distance between point 1, 2 and 3, 3 is absolute value of 1 minus 3. This is 1 minus 3 plus 2 minus 3, absolute value of 2 minus 3, which is basically 3. Okay. And then let's say this is the map we use. We are here, we would like to go to here. Okay, this is x1, y1, this is x2, y2. And if we use Euclidean distance, it is the one with the blue line. Okay, it's the shortest line. So we have a helicopter in order to go from this point to this point. But if we have a car instead of a helicopter, we need to follow the roads, right? So this is the Manhattan distance. Just remember this map, and then you will be remembering the difference between Euclidean distance and the Manhattan distance. And there is yet another distance metric called Chebyshev distance that works like a crane that we use in ware stores. Okay, or you can imagine the moves like the moves of a king in chess game. Okay, in chess, a king moves either diagonally like this, or it can go in this direction, or it can go in this direction. Okay, so for this example, we want to go from point A to point B. The king moves here, and then the king moves here. All right. And in machine learning, the Chebyshev distance can prove useful when you have many dimensions to consider, and most of them are just irrelevant or redundant. And the Chebyshev distance between point 1, 2 and 3, 3 is simply 2, because it just takes the maximum between absolute value of 1 minus 3, which is 2, and absolute value of 2 minus 3, which is 1. So basically the Chebyshev distance between these 2 points is simply 2. Okay. And something to remember, all these 3 distances, Euclidean, Manhattan, and Chebyshev, they're all called Minkowski distance types. Okay. That's a distance type family. This is the general formula for Minkowski distance. And depending on the value p, if p is 1, you have this formula, right? And if p is 1 in here, then it is Manhattan distance. If p is 2, then it is Euclidean distance. And if p is infinity, then it is Chebyshev distance. Okay. And just to sum up these distances and the difference between these distances, what would happen if we want to calculate the distance to our 8 neighbors? Okay, we are here and we would like to, for example, calculate the distance between this point and this point. If we use Euclidean, then in order to go straight, the distance between here and this cell is 1, but the distance between this cell and this cell is 1.4. Okay. If we go diagonally, then the distance is 1.4. If we use Manhattan distance, then if we go straight, then the distance is 1 to our 8 neighbors. But if we go diagonally with Manhattan distance, the distance is 2, because we need to go here, here, or we need to go here, here. So we have 2 moves, okay, if we use Manhattan distance. And the important thing is, with Chebyshev distance, everything is 1. Because remember the move of the king with the chess game? The king can go here, that's 1 move. The king can go diagonally, that's 1 move. The king can go in this direction, and this direction. So everything is 1. So the differences happen if we would like to move diagonally. With Chebyshev it is 1. In Manhattan distance it's basically 2. And in Euclidean distance it's basically, if you're gonna go diagonally, it's 1.4. Okay, let's do another example with our KNN algorithm. That's a new dataset. You can find the datasets in the links. So that's breast cancer Wisconsin diagnostic dataset. Okay, we have these variables, and then in order to load our data, we imported NumPy and pandas. The column names we will be assigning the ID, clamp thickness, uniformity of cell, shape, marginal addition, stuff like this. And then we read with pandas our dataset, and then we check the first 5 rows. As you see, we have an ID, we have clamp thickness, we have uniformity of cell, we have the class. We have the class that we would like to, whether that's cancer or not. This is the target variable. This column is the target variable. These are all independent variables. And as we do usually, we will first take a look at the data. We will try to understand the data with our data analysis phase. We will clean the data if it is required, and then we will do our predictions. Okay. Okay, let's see whether we have any null values. What we observe is we don't have any basically null values. Let's check what we have within our data with data frame.info. So if you take a look at the D type, basically we have integers, and then we see an object. Okay, that's weird because that's supposed to be an integer as well. Okay, and let's try to analyze this bare nuclei column in detail. Then we see something fishy going on. Okay, just to see what we have as unique values in bare nuclei. You see we have a question mark here. That means this is missing data, and we saw how we can basically deal with the missing data in the previous class. But in this class we will just drop all the columns that contain all the rows that contain this question mark, because we just have this question mark, this missing data with bare nuclei. Okay, if you take a look at the rest, we all have numerical values, so there is no missing data in our other columns, but just in bare nuclei we have some missing data. Therefore we will just drop the rows that have question mark. And let's see all the rows that have question mark as bare nuclei. You see it's not that much. I mean, we can just drop this and then we will be fine with that. And in order to drop that, we can drop the none values from a data frame. So we need to replace all these question marks, all these guys, and then in bare nuclei with numpy none, and then we can just use drop none, and then let's check whether anything remaining we have. You see, we deleted all the rows that contains question mark or none as bare nuclei. Okay. So we have the class variable as 1 and 2. We would like to have them as 0 and 1. So this is 4, this is 2 basically. And we would like to get them as 1 and 2. Okay. And if we just divide the class into 2 and subtract 1, what we will get is 1 and 0 for our class. You see we have 444 zeros and 239 ones right now. So we basically divided the class into 2 because we have 2 and 4, and then we subtracted 1 and we came up with zeros and 1. We assign 0 to 2s and 1 to 4s. Okay, that's pretty simple. Let's check the data frame columns. So the thing is, we have something called ID, right? If you look at the data, that's an ID that doesn't represent anything, and that's a pretty big number. If you take a look at the rest, they're quite small numbers, but this is a pretty big number that doesn't represent anything. That's basically a unique definition of the person. And if we use this within our classification, that would confuse the algorithm, because these are so big numbers that will affect everything else. Okay, so we need to drop the ID. This is non-usable. This is pretty different from the other columns. And we need to drop class as well, since we are constructing X. Class is our target variable. It's not an independent variable. So we dropped ID and class and assigned the rest to X. Okay. We will be using the data frame class as our target variable Y. And then, as we do usually, we will use standard scalar in order to standard our data. standardize our data. Okay. So we first need to import that. After we import, we could be able to use it. Now comes the training phase. So we will be splitting our data into train and test, as we usually do. Now we have our independent variables. We dropped ID, remember? We dropped class because it's our target variable. And then we will be splitting our test in a way that 80% of the data will be training and 20% of the data will be used for testing. Okay. And this is a command we explored in the previous example, kneighbors classifier. And in this case, we will be using k as 5. And then this p value, if you remember the metric Minkowski, this means this is Euclidean distance. Okay. If we had p1 here, it was going to be Manhattan distance. Okay. And if that was infinity, that was going to be Chebyshev distance. So Minkowski was the family of the metrics we were gonna use. Okay. And depending on the p value, if it is 2, then it's Euclidean distance. If it is 1, it is Manhattan distance. Okay. That's something we are assigning by hand for now. And then we created our model. In this case, with this command, we calculated our ball tree or KD tree so that we don't need to deal with everything again and again. And then we will be checking basically the prediction scores, the accuracy, the precision and recall values. So this is the function we will be using in order to mass print everything. Okay. And for training, you see we have accuracy score of 0.97. That's pretty high. And for training, again, the precision and recall values for both class 0 and for class 1, they look pretty nice. And for F score as well, we get pretty nice results. Okay. Now let's check whether that's true for the test set as well. You see the accuracy score is quite similar. It's not bad, although this is the test set. And the precision recall values are pretty good as well. And if you check the F score, they're pretty nice. See, that's a pretty good classifier for this example. And if you check the confusion metrics, there are very few false positives and false negatives for the training set, and there are very few false positives and false negatives for the test set as well. But now let's try to use grid search CB. We would like to search within some parameters. Okay. Let's see how many parameters we have for KNN. We do this with get parameters. You see, we have the algorithm. You don't need to search for anything for this. This is just for efficiency of the algorithm. So we had auto, we had ball tree, KD tree, and brute force. And usually it's auto by default, which means if you have too many data, it uses either KD tree or ball tree. If you have few data, then it uses brute force. Okay. So that's leaf size we can search for. We have the metric. We have metric parameters. These are not. This is for using the CPU efficiently, and this is basically the p value for Minkowski distance, and this is basically the k value, number of neighbors. Okay. So the parameters we would like to search for is basically number of neighbors. We would like to use different k values. For k is equal to 1, equal to 2, up to equal to 10. For Minkowski metrics, we would like to try both Euclidean distance as well as Manhattan distance, just to see which one will work better. So we create the variable params. We would like to search within number of neighbors, that's k, and we would like to search within our distance metric. And grid search CV did the calculation for us, so that's gonna take a little bit time, and it basically calculated our best estimator within these parameters. And let's see what's basically the best estimator. You see, it's p is equal to 1. So this grid search CV said, instead of using Euclidean distance, if we had used Manhattan distance, we could get better results. That's what it says. Okay. And now let's print our accuracy score for training. That's pretty high. And let's print our scores for tests. That's basically higher than the one we created previously. Okay. So grid search CV gave us a better classifier by checking some parameters such as k and the distance metric, and it found out that if we use k as 3 and if we use a Manhattan distance, then our classifier can classify this problem in a better way. Some closing remarks on KNN. We have this concept of curse of dimensionality. KNN works well with a smaller number of input variables, but struggles when the number of inputs is very large. Each input variable can be considered a dimension of a p-dimensional input space. For example, if you had two input variables x1 and x2, the input space would be two-dimensional. As the number of dimensions increases, the volume of the input space increases at an exponential rate. So in higher dimensions, points that may be similar may have very large distances. All points will be far away from each other, and our intuition for distances in simple 2 and 3 dimensional space breaks down. This might feel unintuitive at first, but this general problem is called the curse of dimensionality, which actually means having too many independent variables is not something good. If we had, for example, two independent variables, x and y, we would use 2D. Okay, if we had x, y, z, we could use 3D. But the more independent variables we have, the curse of dimensionality starts happening. Okay, the distance measures start losing their meaning. Okay, a few ideas on picking a value for k. We don't have any structured method to find the best value for k, but choosing a smaller k may cause noise, and it may have a higher influence on the results. A larger k will have smoother decision boundaries, which means lower variance but increased bias, but it's also computationally expensive. Another way to choose k is through cross-validation, or we could use grid search CV as we did in the example. So the pros of KNN: it's pretty simple to implement, it's flexible to feature distance choices, it naturally handles multi-class cases, and can do well in practice with enough representative data. The cons of KNN: need to determine the value of k. We need to determine the number of nearest neighbors. Computation cost is quite high because we need to compute the distance of each query instance to all training samples. Even if we use KD3 or BOLT3, the computational cost is higher than other models that may learn. It uses too much storage because you need to get all the data to memory in order to make any calculation for the prediction. And we must know we have a meaningful distance function. And as in the example, we used Euclidean distance, but grid search CVS suggested us Manhattan distance. So we need to rescale the data in order to make the preparation for the classification problem. We need to address missing data. And since the curse of dimensionality affects KNN too much, we need to lower dimensions if it is possible. And we will see how we can lower the dimensions in the next lecture. Okay, in summary, KNN stores the entire training dataset, which it uses as its representation. It doesn't use any model, mathematical model. It uses all the data as its data representation or model representation. KNN is a lazy learner. It doesn't learn anything as a model, as a mathematical model. KNN makes predictions just in time by calculating the similarity between an input sample and each training instances. There are many distance measures to choose from. We have seen the Minkowski distance matrix family. It's a good idea to recycle your data, such as using normalization and using KNN.